Hi everyone, this is Maverick Paul, the chemistry guru. Now in this video, we want to discuss a question involving atomic structure, deducing species with paramagnetism. So let's take a look at this question. When attracted by a strong magnet, some species are able to exhibit paramagnetism. Such species contains unpaired electrons, which are able to spin in a way which aligns parallel to the magnetic field. So which of the following species in a ground state will be able to exhibit paramagnetism? We're given 4 species: O, Al+, Ti2+, copper+. The concept tested in this question, of course, will be under atomic structure. Now, given in the question that species that can exhibit paramagnetism have unpaired electrons, for each of these species, I have to consider the electronic configuration and we see how many of them have unpaired electron. So it's actually a very simple question, just trying to write out the electronic configuration according to the quantum model. In general, the sequence for me to fill up the electrons according to the quantum model will be as such: 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. Now remember, when we are filling up electrons will go to the 4s subshell first, followed by the 3d subshell. But when we are writing down the electronic configuration, we should write down the 3d subshell first, followed by 4s subshell. Then after that, if I have more electrons, the next few electrons will go to 4p6 and so on. Now you notice I've done some highlighting, and recommendation when we fill up electronic configuration, it is easier for me to count the number of electrons if I fill this up by sets of 10. So 1s2, 2s2, 2p6 will be 10 electrons. 3s2, 3p6, 4s2 will be another 10 electrons. 3d subshell actually can hold up to a maximum of 10 electrons, and that will already be 30 electrons. If I need to put more electrons to 4p subshell, 4p can put up to 6 electrons, and so on. You notice if I fill up electrons by sets of 10, then I can actually very quickly write out the electronic configuration for most of the species. I think this will be useful to help us write out electronic configuration very quickly. Now let's run through each of these options and we see which one of them have unpaired electrons and therefore can exhibit paramagnetism. Now the first guy will be oxygen atom. Oxygen has 8 protons and therefore it has 8 electrons. Electronic configuration, if I want to fill up 8 electrons, will be 1s2, 2s2, 2p4. We have to be careful with the valence subshell, which is 2p subshell. There are 4 electrons in my 2p subshell, but it doesn't mean that if we have even number of electrons, then the electrons have to be paired, because if I consider the electron in box diagram for 2p4 configuration, it will be something like this. Remember, according to Hund's rule, when I fill up the electrons will fill up the subshell singly and with parallel spin first. The first electron will go to 2px orbital, spin up. Second electron to 2py orbital, spin up. Third electron to 2pz orbital, spin up. The fourth electron will go to 2px orbital, spin down. So involving my 2p4 configuration, we actually can see that there are 2 unpaired electrons if you draw out the electron in box diagram to really decide how are the electrons arranged and whether do I have any unpaired electrons or not. In this case, oxygen will have 2 unpaired electrons, so therefore oxygen will exhibit paramagnetism. Now how about the second species, Al+? Involving electronic configuration for cations, it is recommended for us to write down the electronic configuration for the neutral atom first. Then we remove electrons from right to left, remove electrons from my valence subshell. So involving aluminum with 13 electrons, electronic configuration will be 1s2, 2s2, 2p6. Again, very quickly I can fill up 10 electrons, 1s2, 2s2, 2p6. Then I just need to balance the remaining 3 electrons, 3s2, 3p1. Involving Al+, what I'll do is I'll remove 1 electron from my 3p subshell. Al+ will be 1s2, 2s2, 2p6, 3s2. And if I consider the electron in box diagram for my valence subshell, which is my 3s2 configuration, 3s2 will be fully filled and the 2 electrons are paired. So Al+ will not have any unpaired electron. Al+ will not be paramagnetic. How about the third example? Third species, Ti2+. Titanium has 22 electrons. Again, what we should do is we should fill up the electronic configuration for 22 electrons first for titanium atom. Then I remove 2 electrons to form Ti2+. So 22 electrons for titanium will be 1s2, 2s2, 2p6, 10 electrons. 3s2, 3p6. Remember, we fill in 4s first, 4s2 electrons, then the remaining 2 electrons will go to my 3d subshell. So the electronic configuration for my titanium will end up to be 3d2, 4s2. And when I remove 2 electrons from my valence subshell, which is my 4s subshell, the 2 electrons in 4s will be gone. So titanium 2 plus electronic configuration will be 1s2, 2s2, 2p6, 3s2, 3p6, 3d2. 3d2 configuration, when we consider the electron in box diagram, 3d subshell, there are 5 orbitals. And if I have 2 electrons, first electron will go to the first 3d orbital, spin up. Second electron go to the second 3d orbital, also spin up. And you notice now I have 2 unpaired electrons for 3d2 configuration. So titanium 2 plus will have unpaired electrons, therefore it will be paramagnetic. Finally, if I consider copper plus. Copper plus, first thing, same thing, we have to write out electronic configuration for copper. Copper 29, based on the 3 rules that we have learned involving writing out electronic configuration for my quantum model, by right, involving copper 29, what I should end up with is something like this. I should be filling up the first 10 electrons, 1s2, 2s2, 2p6, then followed by 3s2, 3p6, 4s2 for the second 10 electrons. Then the remaining 9 electrons should go to 3d subshell. So by right, the electronic configuration for copper should be 3d9, 4s2, but we understand that when we write out electronic configurations, there are actually 2 species that doesn't really obey the 3 rules involving copper. Copper, instead of 3d9, 4s2, it actually prefers 3d10, 4s1 configuration because my 3d10 configuration, my fully filled 3d subshell is more stable. So copper actually prefers 3d10, 4s1 instead of 3d9, 4s2. The other species which also is an anomaly will be chromium. Chromium 24, instead of the expected electronic configuration ending with 3d4, 4s2, it actually prefers an electronic configuration of 3d5, 4s1 favoring half-filled 3d subshell. But coming back to copper, electronic configuration for copper will be 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s1. Copper plus, I just need to remove 1 electron from my 4s subshell. I'll end off with 1s2, 2s2, 2p6, 3s2, 3p6, 3d10 for copper plus. Now, involving 3d10 subshell, if you consider the electron in box diagram, 3d10 is fully filled, so therefore there are no unpaired electrons in copper plus, so therefore copper plus will not be paramagnetic. So we will be able to answer this question already. Which of the following species in the ground state will be able to exhibit paramagnetism? The species with unpaired electron will be number 1, oxygen, number 3, titanium 2 plus. The remaining 2 species will not have unpaired electrons, so therefore they are non-paramagnetic. So the answer to this question will be option A. Alright, so that was the discussion involving this question, identifying which of these species have unpaired electrons and therefore are paramagnetic. So if you have learned something useful from this video, please give me the thumbs up, like this video, and subscribe to my YouTube channel for more weekly video lessons. That's all for now. I'll see you next week.